Conditional probability. You see this type of symbol. So this says the probability of F given E. It means something has already happened. If I am, let's say, drawing a card. So I want to know what is the probability I got an ace of diamonds given I already drew a red card. Okay, this is different than just the probability of drawing an ace of diamonds out of a deck of cards. What would be the normal probability of drawing an ace of diamonds? 1 out of 52. But I have changed it. I've told you I already drew a red card. Now there's still only one ace of diamonds, but if you already knew I drew a red card, how many cards are there that I could have possibly drawn? 26. So instead of being 1 out of 52, it's 1 out of 26 because I already know that my card is red. What would be the probability of getting an ace of diamonds given that I drew a black card? Would it? Okay.
You saw color diamonds.
Yeah, you're on the right track. Okay, if I drew a black card, how many cards did I pick? Or how many cards could I have possibly select? 26. Out of those 26 cards, how many of them are an ace of diamonds? Because it's black. The ace of diamonds is red. If I already told you the card I drew was black, could I have drawn the ace of diamonds?
I was just thinking ace, not ace of diamonds.
So if I told you my card is black, I'm holding a black card in my hand, the probability that I'm holding the ace of diamonds is 0. Because you know that one would be red.
We need to bring
Okay.
I'm sorry. I need to club her black and black.
Are you okay, Abram?
I'm too tired for this.
So, conditional probability. We already know something has happened. And so, when I tell you I have that condition, I am no longer talking about the entire deck of cards. I am only looking at a portion of the cards. So let's look at this one. Suppose a single-sided dice is rolled. What's the probability of a 4? Okay. Now, suppose I roll the dice. So I'm up here with my dice, and I say, okay, I'm going to roll. Oh, I got an even number. What's the probability of a 4 given that I already told you it was even? So if it was even, there were only 3 possible numbers I could have rolled. Only one of those is still a 4. So the conditional probability, the thing it changes, is the denominator. Since I knew it was even, there were only 3 even numbers that I could have rolled. All right, so that condition is your denominator when you set those up. Okay, and that's really what the next slide says. The probability of F given E, the denominator is the probability of E, the numerator is the probability of both. You can just ignore it. It's saying it also works with complements, but we're not really worried about that. We're just talking about basic conditional probability. So, let's look at an example. I think it's easiest if we're talking about problems. A survey was conducted in which 1,017 adult Americans were asked about their beliefs in a higher power. Part A. What is the probability that a randomly selected adult American who lives in the East believes in God? So, I'm asking for the probability that they believe, but what do I already know? What is the condition that I already told you? They are from the East. I want the probability that they believe in God, given that they are from the East. So when I set this up, I already know this person is from the East. So that means I am not looking at the entire table. Okay? I can cover up all of these people. Those aren't who I want. All I care about are the people from the East. So, if I've told you they're from the east, we are ignoring everyone else. How many people are from the east? Out of those 255, how many said they believed in God? So if we divide that, we get okay. Part B. What's the probability that a randomly selected adult who believes in God lives in the east? What is the thing that I know this time? Yeah. I'm saying this time they believe, and I'm trying to find the probability that if they are someone who said they believe that they are from the east. So now, my condition, I know, whoops, that's not what I wanted it to do. I know they said they believed, so I'm only looking at, I don't know what my thing keeps disappearing. These people. So how many total people are there? 787, you said? Out of those, the ones that said, or the ones that were from the east, were 204. And so we get point. So notice the numerator was the same both times. The numerator was people from the east who said they believed in God. That's the same. The denominator is the condition. At the beginning, I knew they were from the east. At the end, I knew that first they said they believed in God. Right? Do you guys understand the difference there? Let's look at this one. In 2005, 19.1% of all murder victims were between the ages of 20 and 24 years old. Also in 2005, 16.6% of all murder victims were 20 to 24-year-old males. What's the probability that a randomly selected murder victim in 2005 was male, given that the victim is 20 to 24? I don't know about you, but when I read those, I get confused. So I start writing down and making notes. So the probability they were between 20 to 24. So the probability they were 20 to 24 years old is 0.191. Also, 16.6 were 20 and 24-year-old males. So the probability that they are 20 to 24 and male is 0.166. I am trying to find the probability that they were male given they were 20 to 24. Right. If it helps you, write out the formula. When I said we were trying to find this condition, so if we look back, the probability of F given E is the probability of both divided by the probability of the condition. So the probability that they were male, given they were 20 to 24, is how many were both male and 20 to 24? Divided by, my condition is 20 to 24. How many were 20 to 24? And so we get 0.8691. These can be really confusing, but if you take a minute and write down the formula you're using and the stuff you have, it helps significantly. Ultimately, at the end, we're basically deciding, am I going to multiply or divide these numbers? Okay, so we can kind of narrow things down from there. This rule turns into the general multiplication rule. So we know and means multiply, right? And we were talking about independent events Friday. that if they had nothing to do with each other, all you had to do was multiply their probabilities. If I take this division statement, if I wanted to rewrite it without a division, I would just multiply over my probability of E. And that gives us the general multiplication rule. Probability of both things happening is the probability of the first times the probability of the second, given that the first already happened. And we could even extend this, they could be flipped. It could also be the probability of F times the probability of E given F. So that might be helpful. You'll just have to look at which condition that you are given when you're trying to set this up. But it's basically your probability times the conditional probability to get both. So if I look back at this example, if I had used the same scenario but kind of rephrased it, 19.1% were between the ages of 20 to 24, so the probability there 20 to 24 is 0.191. 89% were male, given that the victim was 20 to 24. So probability male given 20 to 24. 0.869. We are trying to find the probability that they were 20 to 24 and male. We're looking for the and. And means multiply. So it's just probability of the first one times probability of the second, given that the first occurred. If you wanted, you could even write out in formula form. So we get 0.16597, so 0.1660. Yes.
So why would we multiply this one and divide the last one?
It was a difference in what we were trying to find. This time we were trying to find the and. In the previous one, I was looking for the conditional. So it
Okay.
just depends on which one you need. Other questions? Let's keep practicing. Suppose that of 100 circuits sent to a manufacturing plant, 5 are defective. The plant manager receiving the circuits, randomly selects 2 and tests them. If they both work, she will accept the shipment. What is the probability she rejects it? So what would make her reject it? Hmm. Well, she's only selecting 2 of them. And she'll accept it if they both work. So she would reject it if the first one was defective, or the second one was defective, or they're both. Would it be easier to find all 3 of those, or just the probability of accepting it? Probably the probability of accepting. And then how would we get the probability of not accepting?
Subtracting it from
Mm-hmm. Okay. So the probability she accepts it. That means the only way she accepts it is if they both work. This is a conditional probability. What is the probability the first one works? How many working circuits are there?
95.
There are 5 bad ones, so there's 95 good ones out of 100. Okay, here's what makes this conditional. She took the first one out and tested it. Did she put it back in and then draw a second one? No, this one's sitting on the table. So when I come back, if I took out a good one the first time, how many good ones are in there?
4.
Out of how many total?
99.
99, because we already took one out. Okay. So she will only accept this 0.020. So the probability that she rejects it is just 1 minus that. So 0.098. So she will reject this about 9.8% of the time. Is that okay? Let's try another one. Of 3,215 individuals surveyed, 130 agree with a recent bond issue. Part A, suppose we randomly select one out of the 3,215. What's the probability he or she will agree with the bond issue? What would we do? Red. 0404. If two are selected, what's the probability they both agree? So the first agrees and the second one agrees. And means multiply, right? What's the probability the first person agrees?
0.0404.
Yeah, I'll do it as a fraction, but just to visualize this. Okay, if the first person agreed, when I go to talk to my second person, I'm not talking to that first person again. I am picking someone new. So we get 0.0016. Okay. This was assuming dependence. Basically, I'm standing there and I'm talking to two people. Would I talk to the same person twice? No. If Naren and I both go out and do this survey, is it possible we would select the same person to talk to? Yes. So assuming independence means it could be the same person both times. And that's how we were working problems Friday. If they were independent, you just took the same probability. Okay, so if they were independent, what would we have gotten?
Can we just take 0.0404 squared?
Yes. If you only round 4 decimal places, these look the same, but I think there is a difference. This is like 0.1635 and this was 0.1623. Very similar probabilities. And that's because the sample is pretty big, 3,215. If you had a small sample, they would be more different. The bigger your sample gets, the closer those probabilities are. All right. In general, if the population, if our sample is less than 5% of the population, we treat things as independent. That will be something that we use in the next unit, but I thought I might mention it here. So as long as your sample is less than 5% of the total population, we can assume it's independent. All right. I want you guys to take a second and see if you can set up these two problems. We have 1,000 computer chips. 50 are defective. So what's the probability that 2 selected chips are defective using conditional probability? And what about the second one?
49 over 9,900. So that's decimals.
Lots of decimals. Yeah, our sample is pretty big. So it tells me 2.45 e negative 5, that moves my decimal back 5 places. So it's 4 zeros, 245. What if I assumed they were independent? Instead of me standing there and selecting 2, one chip gets selected at one point and somebody else picks a chip to test later on. What would we do? 50 out of 10,000 square.
$2.5.
2.5 e negative 5, so 0.4 zeros, 25. Is that okay? So these problems, I think it's easier when we're talking about those scenarios like computer chips. Okay, it's easy to think 50 out of 10,049 over 9,999. It's more complicated when you just have formulas and you're not actually thinking about real world situations. So I just want to practice manipulating these formulas a little bit and then I'm done. If I set the probability of A is 0.7, the probability of B given A is 0.4. Find the probability of A and B. Worst case scenario, you are picking up your formula sheet anytime you get confused. All right, we are now, you have to flip around the second page. And I'm looking for a formula that involves these. So if I go down to the first end of that first column, it says the probability of E and F, which in my case I'm just doing A and B, equals the probability of A times probability of B given A. Okay, so look at your formula sheet when in doubt. Write out a formula. You don't have to on all problems, but a problem like this, it might help. Probability of A is 0.7. The probability of B given that A already happened is 0.4. So if we multiply those, we get 0.28. I could use that same formula to help here. The probability of A and B. I have the probability of B, so this would have to be A given that B already happened. So if I plug in A and B is 0.4, probability of B is 0.5, times probability of A given B, so what would we do? Divide. So 0.4 divided by 0.5? 0.8.
So we just divided 0.4 divided by 1.
Mm-hmm. This one. All right. Look at our formula sheet. Do I have a formula that has all of this stuff in it? No. All right, my probability of A or B is probability of A plus probability of B minus probability of A and B. To find probability of A given B, that's the AND formula. Since I'm given B, I have to do probability of B times probability of A given B. So these are the formulas that I have, and you can get these straight from your formula sheet. This one is going to take a couple formulas to get there. So A or B is 0.66. Probability of A is 0.4. Probability of B is 0.3. Times probability of A and B. So if I subtract over my 0.7, divide by -1, so now I can carry that over here. Probability of A and B is 0.04. Probability of B is 0.3 times probability of A given B. So 0.04 divided by 0.3. Get 0.1333. Is this going okay? Understand how I'm getting this? Last one. The probability of A or B is 1. What does the line across the top mean? Yeah, it's that complement, remember, so it's the opposite. So it's not A and B. It's 0.7, and probability of B, of not B, is 0.4. So how would I find the probability of B?
1 minus 0.4.
The complement is 0.4, so subtract that from 1 and we get 0.6. Okay.
So then, that means point A is 0.4.
Not necessarily, because I don't know if they're independent. But,
Well, but
or that they're
point
mutually.
A or B, or whatever, what's being do, point P, A or B, so that'd be A
One.
plus B is
Minus.
1, minus this 0.6 is 0.4.
Okay. But we don't know that they're mutually exclusive, so it has to be the probability of A plus the probability of B minus the probability of both.
Can you plug them in, the questions?
Like,
Like you put 0.6 into P, A, or 0.6.
yes. But you're missing one piece here. That, remember, if I'm doing the or, we have to subtract off the overlap, we have to subtract the people we double counted. So if the probability of not A and B is 0.7, what is the probability of A and B? So A or B is 1. We don't know the probability of A. Probability of B is 0.6 minus 0.3. So if I solve that, probability of A is these are hard to wrap your mind around. Just get in the habit, if it's actually like this, just write down the formula. Okay, the problems where there's actual numbers and scenarios, that's when we can think about it. Here we're just manipulating formulas. The probability of A given B. So that shows up in the A and B formula. And it's the probability, since I need A given B, it'd be the probability of B times the probability of A given B. What did we say A and B was?
1.
That's A or B. 0.3. Because not A and B was 0.7. Probability of B times probability of A given. So if I divide my 0.6 over, what's the probability of A given B? 1.5. It's tricky manipulating those formulas, and we will be practicing more of that this week to help get a handle on Big things that I want to note before I stop for today. We have talked about two different concepts, mutually exclusive and independent. Mutually exclusive means they have nothing in common. So the probability that both happen is what? 0. Mutually exclusive means that one thing happening does not change the other. So it would mean the probability of A is the same as the probability of A given that B already happened. So whether this other condition has been met, it didn't change my probability if they are independent. Dependent is when knowing that I have a red card changes the probability that I have an ace of diamonds. So there is a handout posted on Classroom for section 5.4. I want you to work on that. Like I said, I'm not teaching a new lesson for the rest of the week. We are just practicing everything.